Hello everybody, and welcome back to our webinar, Applying the 7 Steps of Data Analysis to Produce a Quantitative Research Study. William Bannon of Stats Whisperer bringing you the presentation. Okay, in this presentation today, we are going to address part of Step 3 of the 7 Steps of Data Analysis, which is checks of data integrity. Specifically, there are 4 checks we need to make. We are going to address check 1, statistical power, and check 2, test assumptions. So again, in our list of 7 steps, we are here next to the 3, step 3, check of data integrity. Now remember our little parallel here with the bachelorette, right? So step 3 in both cases are checks of integrity, right? So with the data analysis on the right, the bachelorette, step 3 was check of data integrity, right? Do the daters have integrity, as in, are they appropriate for the show? Are they appropriate for dating, right? The same thing with data analysis on the left. Step 3 is checks of data integrity, and that's looking at the same thing. Are the data appropriate for our statistical analysis? We're looking at the very same thing in both cases. So consider, checks of data integrity, consider what's the value of a study if the findings are incorrect, right? And I ask this because without careful attention paid to checks of data integrity, most studies will produce inaccurate findings, right? So for accurate findings, consider the 4 areas in which data must be checked. Number 1, statistical power. Number 2, test assumptions. Number 3, missing data. And number 4, the measurement tools. So to be definitive, in order to be sound and credible, a quantitative study must thoroughly address checks of data integrity. So we are going to use sample study 1 to illustrate how to implement checks of data integrity. And why sample study 1? Because sample study 1 employs a continuous dependent variable. When we have a continuous dependent variable, we have many more test assumptions than when we have our dichotomous. So essentially, we need to do all the same checks that we would have done for sample study 2, plus several more checks of test assumptions for sample study 1. So that's why we'll use sample study 1. It's more rigorous, and we have more to do. So let's recall the research question for sample study 1. Are people who live with dogs happier than people who live with cats? And we have our study map, right, for quick reference. On the left, we have our predictor variables, covariate variable 1 and 2, education level and income level, and the independent variable, do you live with a dog or a cat, all drawing arrows to the right-hand side where we have our dependent variable happiness measured on a continuous scale of 1 to 5. Now, the first part of check 1, statistical power. So check 1 concerns, do we have enough statistical power in our study? So the statistical power is our power to reject a false null hypothesis, or our ability to accept a true study hypothesis. In other words, it's our power to detect if there really is a relationship between A and B. It's our power to detect that relationship. And the power goes from 0, no power, to 1.0, 100% power to detect that relationship, right? Without enough statistical power, we can't answer our research question. Why? Well, If we don't have enough statistical power, which is largely related to not having enough study participants in our study, right? That's where we get our statistical power. If we don't have enough study participants, we could say there's no relationship between variable A and B, but there may have been a relationship. We may just not have had enough study participants to indicate that relationship, right? So we'll get into that a little more. But right now you might be stuck still saying statistical power, what? So look at it this way, right? So if I was doing a study on eating fruit and being happy, happy yes, no. So are you more likely to be happy yes if you eat a lot of fruit, right? So suppose you hear about this study and you ask me about it and you ask how many people I have in my sample, and I tell you 4. I have 2 happy people and they both eat fruit, and I have 2 unhappy people, one eats fruit and one doesn't, right? So you may say to me, it doesn't sound like a very credible study if you only have 4 people in it, right? And you're probably right. So I go to the other extreme and I say, okay, I will recruit 4,000 people so I have a credible study, right? Then I find that 2,000 people are happy who eat fruit, and there's 2,000 unhappy people, and 1,000 of them eat fruit, and 1,000 of them don't eat fruit. And you may say, wait a minute, 4,000? I don't think you need that many. So there the problem becomes 4 people is too little a sample, but 4,000 people may be too large a sample. We don't need that many, right? So just how many study participants do we need, right? So one of the most common ways of determining this is to do a power analysis. That will tell us. So do a power analysis, right? The power analysis is a statistical procedure used to calculate the minimum sample size required to detect a relationship between variables, right? So in other words, how many people do I need to tell if different levels of happiness exist between people that live with dogs and live with cats, right? How many people? So now the power analysis, first of all, keep in mind, it's specific to each statistical test. So we mentioned regression before and t-test. Each test has its own power analysis, right? We'll discuss which to use in a minute, right? But first, let's talk about the software programs you can use to perform a power analysis. Now, thankfully, there's actually software programs online that you can actually use at no cost. So one is Power and Precision, right? They have a free 30-day download. And this is kind of the beginning level of doing a power analysis, right? So it's a more simple tool for doing a power analysis. And number 2 is G-Power. Now this was created by academics and actually is put online for free. So you can use it for free anytime you like. And you can see the web address for Power and Precision and G-Power are right here for your perusal. Okay, more food analogies. Okay, so we could say that a power analysis is a dish with 4 ingredients, right? So the first ingredient is statistical power, which we talked about. The second is level of probability. The third is the effect size. And the fourth is the sample size, right? So these are the factors involved in the power analysis. And you will see that when you set 1 through 3, you get 4, right? Because what we're after is a computation of the sample size needed. So we set 1, statistical power, we set 2, level of probability, and we set 3, the effect size. We click compute or calculate, and we get the sample size we need for our study based on those settings. Then you may ask, well, what are the settings, right? That's useful to know. So the first ingredient, statistical power, which we said it's our it's our power to detect that significant relationship, right? It goes from 0 to 1.0. Now, as a standard, it must be at least 80% or 0.80. Now, sometimes this made 0.90 to when it's more rigorous, but as a standard, 0.80 is okay. Okay, so that's what we're going to use for our power analysis right now. Then we have our second ingredient, which is level of probability. Now this may sound familiar because we also have our p-value when we looked at our inferential tests, right? When we discussed statistical significance. And this actually is quite similar to that, right? So what this level of probability is saying is 5% of the time, right, the relationship we have through the power analysis will be by chance, right? Just like the 0.05 for the inferential test is by chance. So this is also called setting alpha. So alpha probability as a standard can be set at 0.05, which we will use here for our power analysis. And then the third ingredient, luckily, we've already talked about effect size, right? Remember, the impact or the magnitude of the impact that one variable has upon another. For example, we might say, does living with a dog or a cat have a small impact on your happiness, right? A medium impact on your happiness, or a large impact on your happiness, right? So it can have a significant impact. Is it small, medium, or large? Remember that conversation. Now, as a default, it's set to medium. So if there's no reason to choose small or large, the default is to set the effect size to medium. We might set it to large if we say have a very expensive intervention and we only care if it has a large impact on the outcome, right, for the people taking the intervention because it's so expensive. So we don't care if it has a medium or small impact, so we might set the power analysis to a large effect size. Alternately, if the intervention is free and very cost effective, we might even set it to a small effect size, right? If that's might be acceptable to us. So also keep in mind you're going to need more study participants, right, to detect a small effect size relative to a medium or large, right? So to detect a large effect size, you'll need fewer study participants. You may need 80, and then to detect a small effect size, you may need, say, 120, right? Depending on the test you're using and the other specificities. But that's also something to keep in mind. Okay, so 1 through 3 are set for our power analysis. So 1, statistical power set at 80% standard. 2, level of probability alpha is set at 0.05 standard. 3, the effect size is set at medium as a default. And 1 through 3 are going to compute to tell us the sample size needed for sample study 1. Now, remember I mentioned that the tests used each have their own separate power analysis. Well, you could imagine it would be quite unwieldy if we did a study and then, or a paper, and a whole paragraph was devoted to power analyses, for all the different tests used, because we might use the t-test and many bivariate tests, right, as well as the multivariate. So generally what's done is a power analysis is done upon the multivariate procedure. So for example, in sample study 1, the multivariate testing, which is also considered where the hypothesis is tested, right, uses a multiple linear regression. So it's acceptable to conduct just a power analysis for the multiple linear regression, right, to make sure we have enough study participants for the multiple linear regression and report that power analysis alone without power analyses for the bivariate tests and so on. So here we have it set for the multiple linear regression. Again, power set at 80%, probability at 0.05%. Now the effect size says medium equals 0.15 because the f squared, which is one effect size for the multiple linear regression, right? For a predictor, 0.15 is medium, right? So we compute these, it'll tell us for what sample size is needed. Now, this is the actual output produced by G-Power. Okay, so you could see on the left-hand side in the green boxes towards the upper left, right, the effect size is medium 0.15, and you can even see the G-Power people were good enough to put the effect size conventions in the blue bottom rectangle. See, and it says medium is 0.15, right? Alpha set at 0.05 in the next line, power set at 0.80, and how many predictors do we have? That figures into the power 2. We can say we have 3 predictors, and let's assume all 3 will be in the regression model, right? So we put that in there. Then in the upper left, right, you see the blue button that says calculate. We click that, and we get the output produced in the large green rectangle. And you can see the final line there says total sample size equals 85. So we need 85 people in our sample. Now keep in mind, that's 85 study participants with data. You might actually have to, try to recruit 100 to get actually 85 people providing data. So keep that in mind too. But what we need here is to end up with 85 people with data. Now this can be stated in, say, the research report or published paper as such. Based on the G-Power estimates of multiple regression, with power set at 0.80 and probability at 0.05, using 3 predictors, a medium size effect, 0.15, would be detectable using a sample size of 85, right? So that's a lot of work for that fancy sentence, but the good news is, right, that's that. That's all we needed was that sentence to enter, right, to indicate that we've done tests for statistical power and that check of data integrity is complete for sample study 1. Now you see in the book for sample study 2, there's also a power analysis for a dichotomous dependent variable. It's actually just as simple. Okay, so 2, checks of data integrity. 2 is test assumptions. Now, when we use multiple linear regression, the assumptions here largely assume what they call equivalence of variances. The residual scores, residuals of scores have to vary equivalently. They can't be lopsided in like size, right? And we'll display that in a moment. But the sample study 2, the binary logistic regression with dichotomous outcome, does not assume an equivalence of variances. So the only assumption made there is C here, multicollinearity, right? So that's why we're doing sample study 1, because there's many more demands put on us. So just remember, when we do sample study 2, all we need to pay attention to here is the multicollinearity. Okay, so sample study 1, the first thing to look at, a normal distribution, A, test of normality. So when we're looking at normal distributions, right, we have to consider a few things. We have to test the distribution of scores to see if it's normal, right? So distribution of scores is if we have 100 people and they all score their happiness on the scale of 1 to 5, and we have scores of 1.0, 1.2, 3.5, 5.0, right? That's a distribution of scores. And it's assumed that they're normal, right? They make that bell shape. Okay, so we're going to go into that in a moment. 2, identifying outliers, right? Which are extremely high or low scores relative to the mean score. And 3, we're even going to talk about data transformations. So this is what a normal distribution looks like, okay? So if you were to give 100 people a test on happiness, right, or to rate them on happiness from 1 to 5, you would figure most people would not be extremely happy 5 or extremely unhappy 1. They'd probably be right around the middle 3, right? So in this distribution, the higher that semicircle gets, the more people are under it, right? So the very, very tip in the middle, that's where most of the people are. And the 0 is the mean score, right? So you would expect most people to have a score right in the middle, right? About 3.0. So if that was the mean score, that 0 would be 3.0, right? And that's where most of the scores would center around. And if you go up in the dots, you'll see between the -1 and +1, which is the standard deviations, that's the spread of the scores, 68% or approximately 2/3 of the scores are within 1 standard deviation of the mean. So if the mean was 3.0 and say the standard deviation was 1, we would say in a normal distribution, 68% of the scores are, the mean +1, 4, between 3 and 4, and the mean -1, so between 2 and 3. So 68% of the scores would be between 2 and 4, right? They'd be clustered in the center there. Now outside, the further those standard deviations go out, the more extreme the scores are. So you see where it has the -3 and the +3, that's where you would get the high scores, such as, the positive high would be 4.8, 4.9 on that 1 to 5 scale. And the negative, for that -3, you would start getting, 1.2, 1.3, right? The extremely low scores. So that's the distribution of scores, right? Now, the trouble occurs, for example, what if we have an overly happy sample, right? And the skew, the peak, instead of being in the center around that 3.0, was skewed to the right, where everyone's pretty happy, and to say maybe the mean is like 4.5, right? Or what if that top was skewed to the left, where people are unhappy, more toward the 1.0 and 2.0 scores? That's lending us to non-normality. And if we were to put a name to it, we would call it poor skewness and kurtosis. Now, what we were just talking about is the skew, right? The skew is when the peak favors one side or the other, right? Making the distribution non-normal. The negative skew on the left is when we were talking about too many happy scores, right? The happiness is too high, right? So it's leaning to the right. And then the positive skew on the right-hand side, the negative score is leaning to the left, right? Like too little happiness. Now, that concerns the peak in the center. Kurtosis concerns the tails, right? That's where we're supposed to have those extremely high happy scores and extremely low happy scores, right? In the tails, right? Away from the center. So kurtosis is concerned with when there's either too many cases in the tails, extreme outliers, or there's too few. So C, so if you look at distribution C, where they have a peak top, right? So the cases that should be in the tails are actually all jammed up in the peak, right? So the tails don't have enough extremely high and low scores, right? So that's poor kurtosis. Distribution A has good kurtosis, right? It makes that semicircle shape, right? So it has a peak, but at the same time, there are scores in the tails. And in distribution B, there's too many cases in those tails, right? So the tails are kind of like inflated to the point where the center doesn't even have a peak. So that's poor kurtosis. So essentially, right, the normality of the distribution is threatened by poor skewness and kurtosis. Now, we just don't look at the distribution and say if it's normal or not, right? We have to test it, right? We have to put some empirical test to it. And one of the main ways people do that in SPSS is they apply the Smirnov test or the Shapiro-Wilk test, right? Now these are commonly used, but you should be warned, they're very sensitive to sample size, meaning if you have a sample below, say, 1,000 or 500, they're very quick to say your distribution is non-normal. And having a non-normal distribution, has serious consequences because then you have to adjust, you adjust your analysis based on that. So you only want to do that if there truly is a threat to normality, not based on an oversensitive test. So in SPSS, this is the way the Shapiro-Wilk and Smirnov tests are produced. Now they say the Shapiro-Wilk is more fitting for a smaller sample size, right? However, right, that is actually the output you get from doing the test. And in this case, usually people like to see, significance below 0.05, but this significance below 0.05 means it's significantly bad, right? You have a significantly non-normal distribution, okay? And you have to adjust for it. So if you have a sample size below, say, like 1,000 or 500 or so, you should have an alternate way of looking at normality as well. For example, you could look at the ratio of the skewness and kurtosis to the standard error of each, right? So what's the ratio of skewness to the standard error of the skewness and kurtosis to the standard error of kurtosis? If the ratio is, say, 2 times or 3 times, then it's assumed to be approximately normal, the distribution. Now this is a good rule and it applies to various sample sizes. Okay, so actually this is done in SPSS right along the same way where we run our frequencies. So let's look at that really fast in SPSS. So if you go to SPSS and we go to our Analyze Descriptive and Frequencies, right? And say we put income level over, and we go, this is what's on the slide, go to the statistics, right? This is where we usually click mean and standard deviation, right? That's what we're going to do later on. But also here, it says skewness and kurtosis. So that's what we want to click. Then we say continue, and then we say paste, right? Again, we're saving our syntax, right? So go to File, Save As, save your syntax. So we could have clicked OK and ran it, but instead we're saving the syntax. And to run it, you just highlight it and click the green arrow. Now we already have the output here, so let's take a look. So this is what the output would say. The skewness is 0.568. The standard error of the skewness is 0.241. So if we divide the skewness by the standard error, we get a ratio of 2.36, as in the skewness is not larger, it's a little larger than 2 times the standard error. So that's acceptable. It's in that 2 to 3 times ratio slot. However, if we look at the kurtosis, it's large, 3.386, and the standard error is 0.478. So when we divide that, we see a ratio of 7. So the kurtosis is more than 7 times the standard error. So it's significantly non-normal. Right? So what can we do about that? Well, one of the things you could do is where we just ran our frequencies, right? Descriptive statistics under charts, right underneath that statistics, you click charts and histogram and show a normal curve, right? So that looks like this. So we go back to SPSS, right? So back to frequencies, and under here, charts, click that, histogram, with normal curve, right? And what that produces is this, right? So we can actually see the distribution of scores, right? So if we want to know where the non-normality is coming from, we can see, and we see why it's the kurtosis, because there's some outliers here in the upper part to the right. There's some outliers above the normality curve. That's what a normal distribution would look like, right? And then here in the low section, there's a big spike of low scores. So there's some outliers that are significantly lower and significantly higher than the mean, and that's what's throwing off our kurtosis. So one of the ways to deal with that would be to identify outliers, right? So if it's not normal, you could always remove the outliers, then retest the variable to see if the distribution is now normal. So there's a few ways so you have to identify your outliers before you can remove them, right? There's a couple of ways of doing it. Two of them are here. So you could say that a score of 3 standard deviations from the mean is an outlier, and identify them like that, or use the stem and leaf plot. So if we did the 3 standard deviation method, right, calling any score 3 standard deviations from the mean an outlier, right? So we would go back to our frequencies. Remember when we clicked mean and standard deviation, right? We just repeat that we just did a moment ago, and we would get this output, right? This is the same output that the skewness and kurtosis is in. Now, we can see the mean for income is 43.25, and the standard deviation is 1.94, right? So what we would do is we would multiply the standard deviation by the number of standard deviations we're using to define an outlier, which for us is 3. Okay? For a small sample, you might consider 2. For a large sample, you might consider 4. But 3 is a very practical number to use. So after we multiply 3 by the standard error, we're going to subtract and add that to the mean to find our interval. And anything outside that interval will be an outlier score, right? So recall our standard deviation, right, for income was 1.94. So we multiply 3 times 1.94, which equals 5.82. Now, on the second bullet, the mean was 43.25. So if we add 5.82, the 3 standard deviations, we have 49.07. So that means any score above 49.07 is an outlier score, an extremely high score. Then we do the same on the next line, where the mean 43.25, we minus 5.82, and that gives us 37.43. So any score, right, for income below 37.43 is going to be an extremely low score. So don't forget, these incomes are measured in thousands, right? So 37.43 is 37,000, right? $430. So within the frequency output, underneath the mean and standard deviation box, right, we have the frequency box. So we can look and see what the individual scores are. So if we look and we apply our 37.43, we can see there's one score, the 37.00, that's below, right? It's an outlier, extremely low, below that score. And there's a high outlier, right? So we look for any scores above 49.07, and we have one score of 52.0 above that 49.07. Right? So that's one way of identifying outlier scores. And then we have the stem and leaf plot. This is a little more simple. So here you just go to Analyze, Descriptive Statistics, and Explore, right? And under plots, you click stem and leaf as such. So we would go to Analyze, Descriptive Statistics, Explore, put Income here, and under Plots, click by default stem and leaf, and then we would paste it and run it, right? And we would get something like this, right? So this is the stem and leaf plot. Now the little circles and numbers outside are the outlier scores. Now it's important to remember the numbers next to the circles, and if it's an extreme outlier, you get a star, right? The numbers next to the circles identify the outliers by the numbers in the data view blue numbered column as such. So you go to data view, right? So if 1 is an outlier, right? Remember next to the little circle said 1, this, right? This 1 is saying that's an outlier, right? If next to the circle there was a 14, 14 would be an outlier for income. So that's one way of easily identifying them. Right? So there we go. So outlier high score, outlier low score. Okay? And then within the box, the line is the median value, and then the little distribution lines above it are the 25% and bottom 50%. Okay, so after you identify the outliers, right, you can use the recode, right, on page 107 to create a variable that identifies those outliers, right? So you could deselect them and then test, test the variable with those outliers removed. You can also create another version of the same variable and delete the outlier scores, manually if you like. So, and then when you do regression analysis, sometimes they say the regression's robust against the outliers. So you could do a regression with the outliers in and with the outliers out, and if the test comes out similarly in terms of significant variable relationships, just leave the outliers in and report that it's acting robust, right? There's more of a concern if the outliers are causing the statistically significant findings to differ. That's all on page 107. So. All right, so once we remove the outliers, right, that was the source of our problem. If we retest it with the Shapiro-Wilk, there's still extremely significant problems, right? It's still saying, significant at the 0.000 level in terms of, non-normality. But now that the outliers are out, remember the kurtosis was our problem? Now the kurtosis itself is valued at negative 1.39. The negative doesn't matter. So if we divide the kurtosis now by the standard error of the kurtosis, the 0.483, right? Now the ratio is below 3. So it's in that 2 to 3, right? Just as long as it's not above 3. It doesn't have to be between 2 and 3. But preferably not more than 3. We see it's 2.88. So now that's approximately normal. Right? So that's what we want. Now, another way that non-normality is addressed are data transformations, right? So data transformations basically mathematically reconfigure the variable. It'll say multiply every case by a certain number, every score by a certain number to spread them out more evenly. Right? Now the problem with that is it complicates interpretation because it changes, say like the mean score. We had that mean score for income. That was the actual mean score among study participants. But if you reconfigure the variable with a data transformation, all of a sudden the mean is changed from what the sample provided, and it's no longer meaningful to report. So it changes the statistical parameters, as per the study participants. So it's kind of, in that manner, it's more of an extreme solution to transform the variables. However, if you did want to transform them, this is the method that's used in SPSS, right? The transform compute variable method, right? So if we were to go to SPSS to look at that fast, we would go to transform compute variable, right? Then we would click arithmetic there, and then the LG10 log odds, put that up there. And if income was not normal, we would put that in there. So that would take the log odds of income. And we would call the target variable, the new variable name, income log odds, right? And then we would just paste it, or we would definitely paste it to make sure that nothing was done wrong. But if we run it, we can actually see, right? Here it is, income log odds. So that's the log odds data transformed version of income, right? So now you can always do the same thing as we talked about removing the outliers, where you could do the regression with the data transformed, right? If it's more normal with the data transformed version, you could do the regression model with the data transformed version and with the normal version, right? The untransformed version. And if the findings are similar, you could just leave in the untransformed version and report it was not normal, but put in the methods that it was also tested with a more normal transformed version, and the findings did not differ, right? You can put it like this. Analysis indicated the variable income evidenced a non-normal distribution. Analysis was repeated using a transformed version with a normal distribution. Findings did not differ in terms of statistical significance. Right? And just put that in the methods, and everything is up to snuff. All right. Multicollinearity. Okay. Two or more predictor variables in the multiple regression model are highly correlated, right? Findings are distorted when there's an unacceptable level of correlation. Now, what does that all mean? So, multicollinearity. So, suppose we had two predictors of happiness. One is age predicts happiness, and one is income predicts happiness, okay? But then, let's assume that age and income, right? So as you're getting older, you're making more money, are both correlated with one another at a very high level, okay? So correlation equals 0.90. It only goes up to 1.0, so that's high. So this might be the situation. It may be a true finding that age is significantly correlated, significant, p less than 0.05, with happiness. Right? Let's assume that's true. Then it might be the case that income is significantly correlated with happiness. P is less than 0.05, right? So you have two significant relationships. However, the high correlation between them both, between the two predictors, between age and income, might mess up the analysis where they cancel each other out. So then it looks like neither one is significantly related to happiness when they both really are. And it looks like neither one is because the two predictors are kind of fighting amongst themselves, right? They have a high correlation. So if you did this test and you saw both were not significantly related to happiness and you didn't test for multicollinearity, you might assume there's no relationship there between the predictors and the outcome, when really the two predictors are canceling themselves out. So we always have to check for the multicollinearity. So there's a function in SPSS that will tell us if multicollinearity exists, right? So it's generally measured by tolerance values and the inverse of the tolerance value, the VIF, right? So tolerance is not a problem unless it's less than 0.20. and it's a major concern if it's less than 0.10. The VIF should not be more than, say, 2.5 or 3.0. That's pretty high. They should mostly be around 1.0, right? So these are simple indicators of multicollinearity. So you look at it in SPSS through this, right? This path, right? So that's rather simple to do. So you just go to SPSS, right? And when you go into your regression, linear regression, say you put your happiness up here and your, say, income level and age here, then all you need to click under statistics is collinearity diagnostics, right? Continue, and then you would paste it and run it, right? Then you would get your output, which looks like that. It's on the back of the regression model in the output, right? So we notice that the tolerance is high. It's definitely not below 0.20, and the VIF is fine. They're all around 1. So that indicates that there is not significant correlation between the predictors, right? Now, a word of caution. This mostly refers to two continuous variables being correlated with one another, like income and age. However, you'll see education, which may be categorical, is also down there. So normally the categoricals don't have a lot of correlation in my experience, but when they do, I find it is worth looking at and trying to limit any correlation between whether they're continuous variables or categorical. You know, to make an examination if they're having a negative impact on your findings, as we discussed. Now, linearity, right? So if we're doing a linear regression, we're looking for a linear relationship, right? So we have our continuous independent variable, say if income was an independent variable predicting happiness, right? It'd be appropriate for a regression model if it had a linear regression model, if it had a linear relationship, right? So now on the far left here, we see a positive linear relationship, right? As the scores from on X, right, go 1 to 2 to 3 to 4 to 5, the scores on Y also go 1, 2 to see where they see 2 and 2 meet, 3 and 3 meet, 4 and 4 meet, 5 and 5 meet. That's a linear relationship. A positive one is one goes up, the other goes up. The next is a negative relationship, right? So as the one is going up, the other is going down, right? Now the last one is a curvilinear relationship, right? So that's no good for linear regression. See, it starts going up together, and then it starts going down. So this one's increasing, this one's going down from this point on, right? So we have to test linearity to make sure there's a linear relationship, right? That we're looking at an appropriate linear relationship to test with linear regression. Now, we're going to do that the same way we're going to look at our homoscedasticity. So the homoscedasticity also refers to the equivalence of variance between data points, right? If they're spread out evenly, like homogeneity, right? The sameness of the spread of residuals. Now, we could do that also in our regression, right? So when we do our regression, the way we just did, we could put the z-pred and z-resid plot, which looks like this. So we go to analyze again, back to regression, back to linear. This time we click plots, right? And we put in z-pred by z-resid. There you go, continue. And we'll paste that And we'd run that if we needed, but we do not because we have our output here. Okay, so this is the figure that's produced, right? So you have the regression standard residuals on the bottom, the regression standardized predicted values on the side here. Now what you want is a nice even spread, right? So that shows good linearity and homoscedasticity, right? A random dispersion of dots around the zero. So here's the zero, and they're all kind of floating around without crashing into one another for the most part. Now, if it looked like this, like a funnel shape, right, that means the residuals are favoring one side, right? There's not an equivalence of variance. There's a variance over here and not so much over here, right? So that's a violation of the homoscedasticity, right? Next, if it looks like this, remember our curvilinear, right, relationship, if it looks like that, that's not good linearity. So that's a violation of linearity. And to address that, if that occurs, many people perform the data transformation, to spread out the residuals again. They try to address it in that manner. So that's another way data transformation is used. All right. So lastly, we addressed outliers already, but these are especially insidious in this analysis. So we want to talk about the undue influence of outliers, right? So the outlier, as we saw, is a point that's distant from the other observations. It's either extremely higher than the mean or extremely lower than the mean, right? So if the average score is 3.5 and our happiness is measured 1 to 5, right, the outliers would probably be scores around 1.0 and 5.0, right? So it's important to keep in mind, especially in a smaller sample, that even one outlier can produce a false finding, right? So a checks of undue outliers is a must, right? So remember how we said create a filter variable where you can identify the outliers, or a second version of the variable where the outliers are removed, right? That's a must. Let me show you why. So let's say we did a t-test, right? Examining if people that live with dogs or cats are extremely more or less happy. Now we see here, there's 47 people that live with a cat and 53 that live with a dog, right? And the mean for the cat people is higher, right? And the dog people is lower. And we can see under the significance, it's less than 0.05, so it's a statistically significant finding that one is happier than the other. Now, if we just throw, so this is the actual analysis, just throw 3 outlier scores of extremely low for the cat and high for the dog, just 3 in each. So now we have 50 people living with a cat and 56 living with a dog. But now the significance level is greater than 0.05, 0.09, so it's no longer statistically significant. So what we're seeing here is 3 outliers in each group masked that original true finding where there was a significant difference between happiness for the groups. So you see, if this was the finding and we didn't remove those 3 outliers from each group and retest, we would never see that true relationship, right? And it could be the other way too. There could be 3 outliers making the finding significant, and that's not a true finding. That's a finding based on anomalies. So the outlier scores can make it look significant when it's not, or not significant when it is, right? So the big question is if a researcher conducted parametric tests and did not check for the undue influence of outliers, how can we be sure the findings are not errors based on outlier scores? And the answer is we cannot. That's why these checks of data integrity are so important, as time consuming as they are, right? So anyway, So out of our 4 areas of checks of data integrity, we've done 1 and 2, statistical power, test assumptions, missing data and measurement tools will be for the next class, right? And not to sound like a broken record, but checks of data integrity are necessary to find a study credible, right? The quality and future of statistical research hinges largely on making these important checks of data integrity. You'll see they're largely neglected. It's hard to find a published article that actually mentions each one, even where it's appropriate to, which is most of them. Right? So next class, steps 3 and 4, missing data and measurement tools within checks of data integrity. And that's still at step 3, check of data integrity. Okay, thank you for watching, and I will see you at the next class.